Thailand and Burma, which is a small tin granite system with the name of Pilok. And there you see this is scatter distribution. It's clearly not a linear distribution. This you can understand as a linear distribution, but this clearly is a scatter. And this actually, scatter distribution is what we need to explain any hydrothermal process. Because the scatter means there is something missing. This is how I interpreted it. There is something missing from the rock. I would argument that these rocks were originally aligned along this line, but on hydrothermal alteration, they lost tin which is now in the vein systems. It must come from somewhere, which means there must be depletion somewhere, and I would interpret this as the right picture. Yeah, this is a very good observation. I made a geology paper out of this a long time ago, and people still accept this. Well, if you look at uranium, this is also interesting. Uranium now is or uranium deposits, they're also very interesting. Uranium can move in rainwater easily, because it's highly soluble under oxygen conditions. And this is why in a rock you cannot expect the igneous uranium pattern, because uranium is easily moved out by any kind of water at any temperature. But what we see here is that all these rocks which I showed you before, including Makusani, by the way, which is now here, all these rocks have elevated uranium contents, but you don't see a trend. It's all a scatter. The scatter distribution at elevated level. The bulk crust plots down here. Bulk crust has about 2 ppm uranium. But here these rocks have about 10 ppm, but with a large scatter, which means there is uranium enriched, but we just cannot trace the igneous evolution of this uranium because it's so mobile. And by this way you could now go for all elements, and think about it. And you can also use different, for instance, many people like zirconium-hafnium ratios or niobium-tantalum, and then you see this is the bulk, this is the many granites, that's the average granite plots here. But our rare metal granites, they plot here towards the corner with very low niobium tantalum and low zirconium-hafnium. Yeah, this is chemical evolution of granitic minerals. This is about the same. This is niobium tantalum versus tantalum. So these are the rare metal granites. They will plot down here. And there's also Makusani somewhere. Makusani must plot down here. Over in France plots also here highly evolved. So these highly evolved granite systems, they have tantalum enrichment, which goes together with a decrease in niobium-tantalum ratio. And then you can also do this with element patterns. In the Erzgebirge, they distinguish between older granites and younger granites, and these span a time span of about 20 million years. Or 10, it's 10 million years. Okay, doesn't matter. These are older, these are younger. And you see these younger granites, they have an increasingly negative europium anomaly. And the negative europium anomaly relates here to plagioclase fractionation, because plagioclase takes out europium. Here comes another of my traditional favorites. Actually, this was my first paper in economic geology in 1982. And I collected data from the literature all over the world and looked at the tin values with respect to titanium. Titanium I use as an indicator of fractionation. And then I made correlation lines for all these many samples, and these are the different correlation lines. And I noted that tin granites have a slope like this for tin, because the analytical geochemistry was not so much developed in this time. And tin was usually not analyzed in bearing granites. But I noted that non-tin granites have this pattern, which means with fractionation, no tin enrichment, and others have tin enrichment with fractionation. This is what we call a tin granite, and this is what we call a non-tin or average granite. And then I could also show that the correlation lines go back here to average crust, average shale composition. So there is no tin enrichment. Actually, there's another concept around that people think, when they find a tin deposit, there should be a pre-enrichment of tin in the source. But this is nonsense. Yeah, now to understand these different slopes, it's important to know what this guy proposed, Shunsu Ishihara, from the Geological Survey of Japan. Actually, he proposed to distinguish granites into magnetite versus ilmenite series granites. Because he observed that in Japan there are some small molybdenum deposits. They are always related to magnetite rocks, which means granitic rocks which have accessory magnetite. Japan also has a few small tin deposits, and the granites related to the tin deposits, they don't have magnetite, they have instead ilmenite. Ilmenite FeTiO3. And so this difference between ilmenite and magnetite is, in ilmenite, iron is in the 2+ state. And in magnetite, it's in the 2+ state, but also in the 3+ state. So magnetite represents a more oxidized situation than ilmenite. And this is what he wanted to show. Actually, you can write an equation here. Titanite, magnetite, quartz. Actually, on this side is oxygen. So the more oxygen is in the system, the more magnetite is formed. The less oxygen is in the system, the more ilmenite is formed. This is the consequence of this formula. And this is a very important piece, very important part to understand the metallogeny of tin. Actually, we plotted here a number of data also from the literature. In this case, I just use quartz as an indicator of fractionation. This is the most simple. And here, we plotted the ratio of iron 3+ to iron 2+. You know, in the old times, people did wet chemistry and they analyzed iron 3 and iron 2. Today, you usually get just the composite. And then we observed that copper porphyries all have high Fe2O3, FeO ratios, which means there is more oxic iron, Fe3+, than down here. Down here we have all the tin tungsten deposits. I mean the granites related to the tin tungsten deposit. So this is a very important observation. It was copied many times by others. You can also use rubidium strontium. It's the same. But the essential point is here this situation that this ratio distinguishes copper and molybdenum both from the tin and tungsten metallogeny. And this is magnetite series, and this is ilmenite series. And the beauty is you can distinguish these two series in the field. In the field. I mean, you can also use a microscope when you see ilmenite and magnetite, but it's complicated enough. When I travel, I always have this instrument here. This is a magnetic susceptibility meter. It produces an electromagnetic field and it compares the disturbance of the electromagnetic field by a rock with the disturbance by air. And if a rock has magnetite, then the electromagnetic field is disturbed and it gives me the magnetic susceptibility here. And if a rock has no magnetite, then the magnetic susceptibility is low. And then I can say this is an ilmenite series granite. So I can already in the field tell you which granite could be related to tin and which not. Actually with tungsten it's a little bit different. Tungsten is not so much redox dependent. Tungsten granites can also be up here. But tin is very astonishing. Yeah, and the reason for this is given by experimental geochemistry. Let's first look at the partition coefficients again, between minerals and Fersing melt with respect to tin. So this means, this is for instance amphibole, doesn't matter. This is biotype, autopyroxene, spinel, tinopyroxene, and so on. So the guy here, he took some minerals and measured the concentration in the mineral and in the melt phase, coexisting melt phase, as a function of oxidation state. Now I don't know if you know about oxidation state. Actually, it means some people also call it oxygen fugacity. The oxygen fugacity of a rock, of a melt, is defined by minerals, which buffer the oxygen fugacity. And one of these oxygen buffers is the FM2 buffer. Actually, it's the equilibrium between firelight, magnetite, and quartz. If these three minerals occur together, then the oxidation state of the melt is fixed. And if it's more oxic, then we move here to the right-hand side. If it's less oxic, we move to the left side. So this is reduced melts, and this is oxic melts. So in an oxic melt, which means here, there's a distribution coefficient for tin is more than 1, which means tin would go into the amphibole in one way on crystallization. If, however, the system is reduced left to this delta FM cube, then the distribution coefficient changes and the tin remains in the melt. And this applies to all the other minerals as well. So we have a strong dependence of the possibility to enrich tin in the silicate melt, dependence on the redox state of the system. It's just the beginning. So unfortunately, this is you have to again think about this. But this is one of my favorites. Actually, these are experiments again on the solubility of tin in a silicate melt. And I just propose to you that there are different redox states of tin which may control the possibility of enrichment of tin. The different slopes which are observed there, they relate to the ratio of the distribution coefficients of tin and titanium, by the way. I didn't explain this in detail, but it's easy to do. So there seems to be a dependence of the redox state. No, there seems to be a dependence of the redox state of the melt on the possibility to enrich tin, which means on the tin solubility. And this was done here. Now let's think if we have the hypothesis that we dissolve cassiterite in a melt, and then we hypothesize that tin would be in the 2+ state. Then we would have a relationship where the solubility of this tin depends on the oxidation state. Okay? If we don't have this, if we say we dissolve SNO2 in the melt, it remains SNO2 in the 4+ state, well, then we should have no relationship with oxidation state. Okay? And this is what the guy here, this is Bob Lehmann, did. Here is the oxidation state of the system, again expressed as delta, which means the difference to the firelight magnetite quartz buffer. This would be the buffer here. It's quite reduced. It becomes more and more oxide to this side. And this is the solubility of tin in the melt, which you could measure. And then he found this relationship. There's a breakdown here, but this slope here, that's the beauty of experimental geochemistry. The slope is -0.4. With log tin, there is log oxidation state. It's -0.5. And this relates to the following equation. we can, this equation we can write in its equilibrium constant, we can write it like this. Equilibrium constant for this equation is SNO, concentration, times O2 to the times the square, no, not square, whatever. You see it's this, what do you call this in English?
Bracket.
Doesn't matter, but you understand what it is. Divided by SNO2. And SNO2 is has activity 1. This is just 1. Because it's a solid. Because thermodynamics puts this activity equals 1. And then we can logarithmize this equation. And the logarithmic of this K is this O2 expression becomes 0.5 times log O2 plus log SNO. This is 1 and goes out. So this is a logarithmization of this equilibrium constant. Okay, if you are not accustomed to it, it may be not so simple to you. But the point is, you can now write an equation from this, which looks like this. This is solubility of tin in the melt is controlled by minus 0.5 log O2 minus log K. This is a constant here. It's a constant, but here we have, if you think this is epsilon, this is x, this is m. Yeah? We have a linear equation with of the form of epsilon is mx plus b, as you know it from school. Yeah? And this is what you see here. And that's the confirmation that we are that there is the presence of SN2 plus in the melt. While here, no change, this is SN4 plus in the melt under oxy conditions. And this is a very important conclusion, which means now that in reduced melt systems, tin can become enriched. In oxy melt systems, it will not become enriched because it's there in the SN4 plus state. Yeah, this is really a beautiful diagram. Yeah, actually there was more recently, Hans Kepler and Andreas Udita did some more experimental work. They confirmed this line, but they observed that even the solubility of tin is even lower than what Boblin proposed in 1996. But this is a detail which you don't need to know. But now comes the next point. So far I just talked about the tin enrichment in a melt, which depends on redox state. Now we come to the stage where the fluid exhausts from the melt. So now we have to know the distribution coefficient between the aqueous fluid and the melt. This will control how much tin is in the fluid. And this was done here in the experiments. So we have here the distribution coefficient for tin, fluid, melt ratio. And they did the experiments as a function of salinity, because salinity is a fluid is also important, and tin is transported as an Cl plus complex. But also as in relation to the redox state. Actually they used 3 different redox buffers, which you may not know. They did not plot here the firelight magnetite quartz buffer. What they used here is a nickel-nickel oxide buffer. Nickel-nickel oxide is a highly reducing system. And then in between rhenium oxide. This is for experimental geochemistry. And this is a magnetite hematite buffer, which correlates to oxic situations. So which means under oxic situations, the distribution coefficient is low for tin. So you could not expect a strong tin-rich fluid under oxic conditions. However, here, under reduced conditions, the distribution coefficient is quite reasonable. 10 or 20 means we extract most of the tin out of the silicate melt by fluid excitation. Yeah, this is also very nice work which was just published in this year actually. In a journal which you should also know. You should not only know economic geology and mineralium deposita, these are maybe the biggest for economic geology. For geochemistry, there is Geochimica Cosmochimica Acte. This is really a very serious, good journal. There's also chemical journal. So there's lots of journals, but you must really stay with reading. That's important, actually, especially for students. Read as much as possible in the original language. And I think on internet now you can see most of these articles in journals and open access. So there is really no obstacle. So you should sit down, but not at your smartphone. This is duty. You need a screen where you can really read something and look for something, whatever you are interested in. But it's important to look at this international primary literature, not these traditions in Castellano which date from 10 or 20 years ago. Yeah, okay. And then comes now a few other specialties which I will not nominate. But if we now continue with our aqueous fluid, the aqueous fluid may have 700 degrees or so, and then it goes down to 350 or so. So there was also experiments done on the solubility of tin as a result of temperature and as a result of oxidation state. This is a quartz-rhyolite buffer, nickel-nickel oxide, they are quite close together. It's a hematite-magnetite buffer. So you see, if you want to transport tin under oxide conditions, even at 700 degrees, you can only dissolve, maybe 100 ppb or so. So this is a logarithmic scale. This corresponds to 1 ppm. This corresponds to 10 ppm. So under reduced conditions, you can transport much more tin than under oxide conditions. This is what the paradox is. And then there's another point. The solubility is also dependent on pH. I don't know if I have written this here. Actually, the solubility depends on -2 pH. So the more acid the solution is, the better it can transport tin. And this is derived from this equation, by the way. You can write an equation. This is the complex which is most important for tin transport. This is what is precipitated as NO2, and then you just have to balance an equation, it's all. Which means you have to put some oxygen here, and you have here the H plus and the Cl minus. And just from looking at this equation, you can say the more acid the environment is, the more tin can be dissolved. That's the main point. And this is why I put this reddish field here. This is a tin Grice environment. This is an environment of very acid fluids. And in such an environment, we can expect 100 even 1000 ppm in solution. And on neutralization, this will talk, of course, solubility. And this actually is different from tungsten solubility. This is the reason why we often have separate tungsten and tin deposits. Tungsten solubility is different. It's related to this Wolfram and salinity, but there is no dependence on pH and FO2. No dependent oxidation state. And no dependence on pH. So this is why tungsten precipitation works on completely different mechanisms than cassiterite crystallization. Yeah, then I come back here to my favorite, the tin versus titanium versus tin. You see here, this is, I now call this the reference line. And you see again here this situation of the scatter field, and this is what makes me what it was. So there is just tin missing. That's it. Right. This was a paper in Geology in 1987. And the missing tin is then in these sheeted rain systems. It's the same area. It's below granite. So this is where this is our explanation. And other people have observed this also. Alaska, and actually we also observed this in Indonesia. There the granites are very low in tin, it's unbelievably low. Apparently they have lost most of their tin to hydrothermal systems which are not there anymore. Okay, and then comes the hydrothermal evolution. I think it's enough for everybody. I have another 50 or so pictures, but you got the point, or you got some important points. You must not have the full story. Maybe on another occasion. Because I did not yet talk about the Bolivian situation. Which is an exhausting. But I don't want to start this on YouTube. Put this on YouTube. I think everybody is tired of reading myself. So I just thank you for your patience. Great students. And see you on another occasion. Yes, I showed you some other buffers. These are popular with experimental geochemists. There's, for instance, the nickel oxide. If you have the two components together, then oxygen is fixed. Easy. So there's equilibrium. And there's hematite magnetite, which I mentioned. There's equilibrium between these two members. If you have coexistence of hematite and magnetite, then you know you are at the hematite-magnetite buffer, which means oxygen. So just from looking at the minerals, sometimes you can deduce the oxidation state. It's the same, for instance, with the sulfides. This was actually what I wanted to show here. So under reducing conditions, pyrite cannot form. It forms at high temperature. First you form pyrrhotite, and then the fluid continues to evolve, and then the pyrrhotite is destroyed and replaced by pyrite. So in all the deposits here in Bolivia, for instance, you see pyrite, lots of pyrite. But sometimes, if you look under the microscope, you see the relics of the pyrrhotite. Because pyrrhotite has a lamellar texture, crystallographic texture. And you still see this preserved. And usually the pyrite is not pyrite, it's often a marcasite, together with the siderite. And this is, so you can write again in formula, pyrite plus CO2 plus water, pyrrhotite plus CO2 plus water produces pyrite plus siderite and produces marcasite, siderite, and carbonate, iron carbonate. And this is what you can observe actually in the field and under the microscope even better. And this is, all this was observed by Kelly and Tornio. Actually, this is really what I can really recommend to everybody here. If you want to learn about the Bolivian deposits, but about tin deposits in general, this paper is excellent. It came out in Economic Geology. I don't have it here, but in the 1980s, Kelly and Tornio, you must know it, you know it. Yes, because it's a basic paper. They did fantastic work on the mineralogy, on the fluid inclusions, reconstruct the fluid evolution. This is up to today. It's a bit long. But you have to read it sometime. So, other questions?
I have another one. So, is it possible to find tourmaline with lithium mica together?
Yes, it's possible. No reason why not. But it's just empirical. Often you see environments where lithium mica is dominant, and other environments have dominant tourmaline. And in Bolivia, for instance, tourmaline is the dominant mineral. There must also be lithium mica somewhere, but it's not important apparently. But tourmaline is everywhere. And if I would have continued here, I could have shown that the tourmaline receives the boron from the Paleozoic sedimentary rocks. This can be shown with the boron isotope levels. And this is different from the copper porphyries. This makes the story even more interesting. If you go to Chile, do the same work there, then you see that the boron isotope composition is completely different. There it relates to seawater. So in the Chile copper porphyries, it's recycled seawater, what you see in the boron component, while in the Bolivian part, further inland, you see the recycled boron from the basement. So, okay, this is enough? No. Actually, at first, at that time, lithium was quite exotic. Nobody cared about it. And I think maybe we did some analytical work, including lithium. Lithium is enriched, but not to the level to form lithium mica. So what we found in the Chakataya system is muscular, just muscular. Because the Chakataya system is not so highly evolved like a rare metal pegmatite. It's just a rare metal granite.
One question. In the Bolivian deposits that you obtain is Waluni deposit and the Ayagua deposit and Urusia. It's similar in of the world, of different.
Compared to what?
It's different. The deposits of Waluni, Ayagua, Urusia, some all other deposits of the world.
Yes, they are the so-called subvolcanic deposits. Most deposits, like San Rafael also, are related to granite intrusions. And here in the central and southern Bolivia, we have subvolcanic systems. There may be granitic intrusions below, but we don't know this. And these systems are different.
Other questions. The thin and wolfram deposits in La Torre and La Paz is similar to some to graphics.
Exactly, it's the same. You have a granite intrusion, 220 million years. Then you have the vein systems. It's exactly, you also have a triassic system. Everything is there. Yeah, but in this going south, we are at a volcanic to subvolcanic level. It's different. Well, if you want, I can continue, because I discussed these questions. Maybe I just show you a few things. I show you the question, because the most intriguing question in Bolivia for a long time is, where are the highly evolved rocks? Because the tin porphyries consist of dacitic material, which is not highly evolved. So this was also for us was an important question. And I had a project here. Actually, this is from Kelly and Antonio. Kelly and Antonio, 1970 it was. Yeah, then we have the prismatic and so on. Yeah, but by the way, this is this alteration of pyrrhotite by marcasite. This is marcasite, all this stuff. But you still see this crystallographic lineation, which is from the pyrrhotite. There's no pyrrhotite left. But you still see, must have been pyrrhotite. Here also. This is nice. From Chakataya also. Because there's also some gold from time to time.